Good morning. Today we will discuss about a block diagram of a pulse code modulation system. So in this block diagram of a pulse code modulation system, so earlier we have discussed about elements of a pulse code modulation system. Now we will see what is the pulse code modulation system. So generally earlier we have discussed one topic, that is elements of PCM. So elements of PCM we have discussed separately. That means the transmitter separately we discussed, transmission path separately we discussed, and then the receiver section is also separately we discussed. Now what is system? What is the difference between the previous topic and this topic? So here we connected transmission path, transmitter and receiver through transmission path. So this is the block diagram of the pulse code modulation system. So in this block diagram, the first element is a sampler. So what is the input to this sampler? The input to the sampler is a X of t. So this X of t is a band limited low pass signal X of t. So why I am saying it is a band limited low pass signal means, and before applying to this sampler, this X of t signal is passed through a band limited low pass filter. So in order to avoid the aliasing effect, so X of t signal is passed through a low pass filter. So initially before apply to this sampler. So here what happened when X of t signal is passed through a low pass filter or a band limited low pass filter, it removes whatever the unwanted frequency components other than FM hedges. Only FM hedges frequency components are passed, and those X of t signal is applied to the sampler. Now sampler will perform sampling. So it converts the continuous time into discrete time. So in order to convert that continuous time into discrete time, you can see excess of t we are assuming as analog sampled signal. Okay. So in order to convert sampler into its sampled value x of t, analog sample values, sampler will take a sampling frequency fs is greater than equal to 2fm. So after taking fs is greater than equal to 2fm, sampler will produce a analog sampled signal, that is xs of t. X suffix s, that indicates suffix s indicates a sampler output, and xs of t again means it is analog signal only. So sampler will convert x of t into analog sampled values. So xs of t is the analog sampled value signal. Now this analog sampled value signal is applied to the A to D converter. You know, the combination of quantizer and the encoder we can treat it as a to D converter. Here what is the function of the quantizer? A quantizer will produce a quantized output. What is the quantized output in this case? SQ of t equal to xs of t plus EQ of t. So here what is this EQ of t? EQ of t is nothing but a error signal. So whenever the quantizer performing the quantization, there is a chance of getting the quantization error. So while performing the quantization, there is a chance for getting the quantization error in the quantizer. That quantization error we represented here is a EQ of t. So the output of the quantizer is SQ of t equal to xs of t plus EQ of t. So this SQ of t, that is the output of the quantizer, is encoded by the encoder. Here what is the function of this encoder? Encoder just simply assigns ones and zeros to this XSQ of t. So XSQ of t equal to XS of t plus EQ of t. For this, encoder will assign sequence of code words, that is ones and zeros. Now those ones and zeros are passed through the channel, which is a noisy communication channel. So in this noisy communication channel, we are generally placing number of regenerative repeaters. These number of regenerative repeaters are used for the purpose of removing whatever the noise which is added in the channel itself. So in generally, if you transmit any signal through channel, where the noise will occur means the noise will occur in the channel itself. So in order to remove that noise, that means in order to reconstruct the original ones and zeros from the channel uses regenerative repeaters. Here we are placing a more number of regenerative repeaters in order to cover the more distance. So the main element of the regenerative repeater is a one of the main element is a decision making device. That a decision making device will take a decision against the value, that is whether the 1 is received or 0 is received depending upon the value, that is threshold value, which is set by the regenerative repeater. So after that you can see here we have a matched filter. So what is the function of this matched filter? Here the matched filter is used to extract the pulses from the unknown signal corrupted by the noise. Here we are saying that decision device, unlike a decision device, what will happen? Suppose if further any noise is added, suppose if the further noise is present, that further noise will be removed by this matched filter. This matched filter extract only the pulses which are present in the noisy signal. So after that, we are having a DTA converter. The output of the matched filter is a digital signal. Now that means it consisting of the pulses. Now these pulses are converted into analog signal by means of a DTA converter. Now the output of this DTA converter is XSQ of T. So earlier we generated at the output of the quantizer, the same signal will be generated here, that is XSQ of T, and which is passed through a low pass filter in order to reconstruct the original signal X bar of T. Here X bar of T equal to XQ of T, that is a quantized signal, plus NQ of T, that is a quantized noise, and plus N naught of T, that is the noise which is present in the channel. So that is because of the channels and the channel noise. Okay, and NQ is the noise due to the quantization, and N naught is the noise due to the channel. Okay, so this is a block diagram of pulse code modulation system, and there is no need of any confusion. And the previous topic is the elements of PCM. In that elements of PCM, we have discussed separately what is the transmission path, and what is the transmission section, and what is the receiver section. So separately we discussed about the elements. Now here we are discussing the total PCM system by connecting together. That means transmitter is connected to the receiver with the transmission path, that is noisy channel. Now, so in this PCM, one of the major element we need to discuss is a quantizer. So now we will look at a quantizer. So what is a quantizer? Quantizer, it is the process of quantization, means it is the process of converting the continuous amplitude signal into a discrete amplitude signal. So in generally we can also represent it as we can also define the quantization as a representation of analog sample values by a finite set of levels. So here quantization is the process of converting the continuous amplitude signal into discrete amplitude signal, or we can follow the second definition. So because it is very easy definition, and in the actual scenario what we are doing in the quantization is the second line, that is the representation of analog sample values by a finite set of levels. So that is called quantization. Now let us try to take X of T, which is analog signal, in order to understand this quantization process. Signal is then output of the sampler, and the quantizer will be X of KTS. That is KTS means X of T signal is sampled at a rate equal to TS. At the rate equal to TS means multiples of TS, KTS, K equal to 0. So means X of 0, K equal to 1, X of TS, K equal to 2, X of 2 TS, K equal to 3, X of 3 TS, like that. So X of T signal is sampled initially, and the sampled signal is X of KTS. And after that it is passed to the quantizer. Quantized output will be XQ of KTS. So Q indicates the quantized output respectively. Now here sampled signal X of KTS converted into one of the Q number of allowable quantization levels. And here I am assuming that Q number of allowable quantization levels here are M1, M2, M3, M4, and so on, MQ. And these quantization levels are assigned in accordance with the following rule, that is XQ of KTS, that is quantized output is equal to quantization levels MI. So quantization output is XQ of KTS, which is equal to MI, that is number of quantization levels. Here you can see I equal to 1, M1, that is the first quantization level. I equal to 2, that is M2, second quantization level. 3, third quantization level. I equal to 4, M4, fourth quantization level. I equal to Q, MQ, MQ, that is a Q quantization level. So these quantized values are assigned to the output of the quantizer based on this rule. Here, what is the rule that is followed? Here you can understand this condition clearly. X xi minus 1, xi minus 1 is less than or equal to x of kts less than xi. For example, below 1 volts, okay, below 1 volts and up to 0 volts. Below 1 volt, for example, I equal to 1 you can treat, okay. So x1, that means below 1 volt, x1 below 1 volt, and xi minus 1 means x1 minus 1, that is 0. So below 1 and 0, below 1 up to 0, below 1 up to 0, all sampled values are assigned to the quantization level, that is m1. Clear? Now again I am explaining how this quantization level is assigned for the sampled values. Here x of kts is the sampled value, okay. For example, take I equal to 2 in this case. If I equal to 2, this condition will become what will happen to this condition? X2 minus 1, x2 minus 1, x2 minus 1 is nothing but x1, okay. And what about xi, x2, okay. So x1 to x2, here you can see the condition up to x1 and below x2 means x1 to x2 and below x2. So in this below x2, x of kts value, if it is present, then this x of kts all values are assigned to the quantization level, that is m2, okay. So in this manner, the quantizer will assign the quantization levels to the output of the quantizer, and the output of the quantizer is a sequence of levels given by xq of t equal to xq of kts, and where kts is less than t less than or equal to k plus 1 into ts. The output of the output signal to quantization noise power ratio, the output signal to quantization noise power ratio of a quantizer is signal sq by nq, okay. Sq by nq means signal power by noise power at a quantizer, that is sq by nq, which is equal to expected value of xq of kts whole square by expected value of x of kts minus xq of kts whole square. So in the denominator part, you can think x of kts minus xq of kts is nothing but it is a quantized output, that is error signal we can say, okay. Now we will try to concentrate on the types of the quantizers we have. How many number of types of quantizers we have? Generally, quantizers we can say there are two types of quantizers. One is uniform quantizer and second one is a non-uniform quantizer. We can also call uniform quantizer as a linear quantizer and non-uniform quantizer as a non-linear quantizers. So now in this today's topic, we will discuss about uniform quantizers. Okay, so these uniform quantizers are also called as a linear quantizers, and why they are said to be known as a uniform and why they are said to be known as a linear quantizer? Here is one of the important point, that is the step size. So what is this step size? And before going to see what is this uniform quantization, what is the step size here? So the definition of the step size is, for example, let us consider a signal x. Capital X is a random variable. I'm considering a signal capital X, okay, and this is the sampled value, that's why I am representing the random sampled value capital X, okay. The minimum value of this signal x is a, I am assuming, and the maximum value as a b, I am assuming. Now, so if the a is the minimum value and b is the maximum value, then the step size is defined as delta, which is equal to b minus a by q, okay. B minus a by q, we can say upper value minus lower value by q, we can say. That means maximum value minus minimum value by q. Where q is nothing but a number of quantization levels, okay. This step size delta is constant over the complete range of the signals while we are performing the quantization. If we take the step size as a constant value throughout the process, if we take the step size as a constant value, that means a fixed value for the step size, and based on the fixed value, if you perform quantization throughout the process, then the quantization is called uniform quantization. And there are three different types of uniform quantizers. And these uniform quantizers, for these three uniform quantizers, that is the mid-trade quantizer, mid-riser quantizer, biased quantizer. These three are the uniform quantizers. For these three uniform quantizers, you will see what is the transfer characteristics of the mid-trade quantizer, similarly mid-rise quantizer and biased quantizer. Along with the transfer characteristics, we will try to understand what is the quantization error which will occur when we are taking this mid-trade quantizer, and what is the quantization error occur when we have taken this mid-riser quantizer. Similarly, for the biased quantizer case, what will be the quantization error we will try to calculate. Now, see, this is the characteristics, that is the transfer characteristics of a mid-trade quantizer. So in this graph, you can see two graphs are there. The uppermost graph, which is the transfer characteristics, and below we have a like a ramp signal shape. So this one is the quantization error. So if you observe this x-axis, on the x-axis here, especially on the upper graph, we have a quantized output, that is xq of nt, and on x-axis we have x of nts. Now, why it is said to be mid-trade quantizer? That means you can see input x of nts at origin input is 0. Similarly, output is also 0 here, because x-axis is 0 at origin, output is also 0 at origin. Now, see another condition, just below this delta by 2, you can see on the x-axis we have a delta by 2, and then we have a delta, and then what about next one, 2 delta by 2, next 3 delta by 2, 4 delta by 2, 5 delta by 2, 6 delta by 2, 7 delta by 2. There are alternative values I was represented, and no need of any confusion, right? So first one is a 0, that is 0 into delta by 2. Next, that is 0. Next one is a 1 into delta by 2. Next, 2 into delta by 2, 3 into delta by 2, 4 into delta by 2, 5 into delta by 2. So no need of any confusion. And 6 into delta by 2, 7 into delta by 2. So that means here here from 0 to delta by 2, if you observe, that means when the input x of nts is just below delta by 2, when input x of nts just below delta by 2, the output of the below delta by 2 means this is the area. Below delta by 2, up to delta by 2, its value is 0 only. Output of the quantizer is 0 only up to delta by 2. That means below delta by 2, you have to take. Okay. And yet just delta by 2, its value is delta. Okay. That is just delta by 2, its value equal to delta. Means when the input is delta by 2, at delta by 2, the output of the quantizer is plus delta, because on y-axis we have a delta. Okay, so it is plus delta. And next, observe here, below minus delta by 2. Okay, when the input is below minus delta by 2, when the input is below minus delta by 2, here also the output is 0, and just at minus delta by 2, its value equal to minus delta. Okay, so here you can compare the output based on the input, means compare the value of x-axis with y-axis. Based on that, you can explain what is this mid-trade quantizer. I am explaining like this, like input is minus delta by 2 here on the x-axis, because x-axis values are input values. So up to minus delta by 2 means, up to means below minus delta by 2, and there is no output, means y-axis there is no value, and exactly at minus delta by 2 we are getting the output of the quantizer, that is on the y-axis, that is minus delta. So the output of the mid trade quantizer will be, you can see, you can understand with this concept. At 0 its value is 0, up to delta by 2 its value is 0, up to minus delta by 2 its value is 0, just delta by 2 its value is delta, at just minus delta by 2 its value is minus delta. So here is the here you can understand clearly. See, when the input is in between minus delta by 2 and plus delta by 2, then the quantizer output is 0. Okay, for minus delta by 2 less than x of nts less than delta by 2, xq of nts value is 0. Here delta is a step size. Similarly, at delta by 2 less than equal to x of nts less than equal to sorry, less than 3 delta by 2, xq of NTS value is delta. Similarly, other levels are assigned. So it is called mid-trade quantizer. Output is 0 when x of NTS is 0. Okay. And now we will try to calculate what is the quantization error in case of this mid-trade quantizer. So the output of the mid-trade quantization error is epsilon. We are representing the quantization error. Quantized output minus a sample output. That is xq of NTS minus x of NTS is the quantization error. Now, so from the above characteristics, what we can observe when the x of NTS is 0, xq of NTS is 0. In that case, quantization error is also 0 at origin. When x of NTS equal to delta by 2, the quantizer output is just before this level. The output of the quantizer is just before this level. Hence, the error is delta by 2 near this level. Okay, because just before means output is delta by 2. So its value is minus delta by 2. So minus delta by 2 less than equal to epsilon less than equal to plus delta by 2 is the range of the quantization error present in the mid-trade quantizer. So thus the quantization error is lies in between minus delta by 2 to plus delta by 2, and the maximum quantization error in case of this mid-trade quantizer will be modulus of delta by 2. So here you can understand one of the important point from these calculations. What is the quantization error of a mid-trade quantizer? So maximum in online examination, this type of question are commonly occurring. So this is error quantization. So what is the quantization error which is present in the mid-trade quantizer? That is delta by 2. Okay. And the xq of NTS, you can treat this one. Input is 0, then quantization error is 0. Quantization is also 0. And at delta by 2, input is delta by 2. That means when input is delta by 2, output is delta. So delta minus delta by 2, we can treat it as a delta minus delta by 2, we can treat it delta by 2. That's why we are getting minus delta by 2 and plus delta by 2 values, right? Now, coming to the mid-riser quantizer. Now, you can examine this mid-riser quantizer. And one more important point in this characteristic mid-rate, here you can see one dotted line is there. That is the ideal transfer characteristics which is passed through the this 0 point. And here we have a step signal. Like we have a some around 7 steps are there, which is called staircase output, because the output of the quantizer is a staircase signal, and the size of this stair is nothing but a step. Stairs means steps, right? And the size will be a delta. So the size is constant throughout the process. Next, mid-riser quantizer. Here also dotted line is there, which is ideal characteristics and staircase output. So here you can see what is the maximum error quantized values for this case. Also, it's a delta by 2 only. And you can see here when the input is 0, the output of the quantizer will be either plus delta or minus delta by 2. Okay. When the input is x of NTS is 0 at origin, the output of the quantizer will be plus delta by 2 or minus delta by 2. And from 0 to delta, that means when the input is delta, when the input is delta up to delta, its value is delta by 2. When the input is up to minus delta, its value is again minus delta by 2. So you can understand the conditions like this. For 0 less than or equal to x of NTS less than delta, output of the quantizer xq of NTS equal to delta by 2. Minus delta less than or equal to x of NTS less than 0, xq of NTS equal to minus delta by 2. Similarly, when an input is in between 3 delta by 2 and 4 delta by 2, the output is 7 delta by 2. So this is called mid-riser quantizer because its output is either plus delta or minus delta when the input is 0. Okay, the output of the quantizer is either plus delta or minus delta when the input is 0. Now the quantization error will be delta equal to xq of NTS minus x of NTS, that is delta by 2 minus 0, because at 0 it has a value delta by 2. So delta by 2 minus 0, which is equal to delta by 2, and another value minus delta by 2 minus 0, that is minus delta by 2. So So the quantization error is lies in between minus delta by 2 and plus delta by 2. So the maximum quantization error will be delta by 2 only. So here you can see in both the cases, in both the cases, in mid-riser quantizer and mid-rate quantizer, the dotted lines of the dotted line of unity slope passed through origin. It represents the ideal non-quantized output input-output characteristics. So when we pass the input signal through the quantizer, so the staircase characteristics is an approximation of the line. Means before quantization, we have a dotted line that indicates a dotted line. After performing the quantization, it represents the staircase. The difference between the staircase and the unit slope line represents the quantization error. Next, coming to the next quantizer, that is biased quantizer. Here also this biased quantizer, you can understand. Here also we have ideal characteristics as well as a staircase characteristics. On y-axis we have a quantized output. On x-axis we have a sampled output. Here exactly when the input equal to 0, the output is 0. Okay, output is when the input is 0, the output will be minus delta by 2. When the input is up to delta, when the input is up to delta, the output is delta. So to understand clearly what is this biased quantizer, see these are the conditions. The mid-riser and mid-rate quantizers are rounding quantizers, we can say, but the biased quantizer is a truncation quantizer. It is clear from the above diagram, when the input is 0, that is between 0 and delta, the output of the quantizer is 0. That is 0 less than equal to x of nts less than q, xq of nts equal to 0. Similarly, for minus delta less than equal to x of nts less than 0, xq of nts is minus delta. So from the characteristics, when the input is delta, output is 0, hence the quantization error will be epsilon equal to xq of nts minus x of nts. That is output is 0 at input delta, so 0 minus delta, which is equal to minus delta. So that the quantization error lies in between two values. One is a 0 value and second one is the minus delta value. So minus delta less than equal to epsilon less than equal to 0. The quantization error in case of biased quantizer is delta, which is the maximum quantization error. So the maximum quantization error will occur in case of biased quantizer, but we require only the lower values we need to take. So it is better to prefer the previous two versions than this biased quantizer. As the quantization error is more in biased quantizer compared to the mid-riser and mid-rate quantizer. The end slope dotted line passed through origin. It represents the ideal nonlinear transfer characteristics. The difference between the staircase and a dotted line gives you the quantization error. So the quantization error is more in case of this biased quantizer. So we need to take the previous two quantizers, mid-rate and mid-riser quantizer, for the purpose of performing this quantization in case of our pulse code modulation system. Or in general, we need to consider the quantizers whose quantization error is low. So in the next class, we will discuss about what is the signal to noise power ratio that is present in the pulse code modulation systems. There are a number of steps to derive the signal to noise power ratio and the quantization noise in case of pulse code modulation system. Thank you.